And then next up we have Hansen, who is, I believe, presenting virtually. Yes?
Yes.
Yep, and then whenever you're ready, go ahead and get started.
All right, perfect, thank you. Welcome to my talk about semantic features of object concepts generated with GPT-3. My name is Hansen. I'm an undergrad student with Martin Hebert at the Max Planck Institute for Human Cognitive and Brain Sciences. So let me first start with a short explanation of what semantic features are. Semantic features can be seen as minimal descriptions of concepts capturing their semantic meaning. They've been playing a central role in investigating the nature of our conceptual representations, where the meaning of concepts can be defined by the overlap and differences of semantic features. These features have been used in a variety of research areas, from cognitive psychology to computational linguistics. So how would you, for example, describe a dog? We could say it has 4 legs, or it is an animal, or it has a tail, or it barks. And how would we then collect these semantic features? A common approach would be to instruct humans to just simply list semantic features, for example, by asking, what are the properties of a dog? This was already done in previous studies that led to the creation of human-created semantic feature norms, for example, the McRae and the CSLB norms. These norms provide high-quality features and are used as gold standards for human conceptual knowledge. But the problem with these norms is that they have a limited number of concepts covered, and the collection and norming of new features is costly and time-consuming, as it requires collecting responses from human participants. Therefore, our goal was to leverage recent advances with large language models to generate human-like features for arbitrary concepts. The idea is that as recent models can achieve high performance in many natural language tasks, like sentiment analysis, for example, they might be capable of generating sensible semantic features. Previous work already investigated methods to create semantic features. For example, Bafia and Ritchie used a fine-tuning approach based on the BERT model, where the model has to predict whether a feature and a concept belong together. The approach is also built on top of a large language model, but requires probing existing feature-concept pairs. Derby and colleagues proposed a method to project semantic features into a word embedding space. With this approach, features can be created for new concepts, but only using existing features from human-generated norms. Here, we try instead to use text generation to generate completely new features for any concept. For this purpose, we chose the GPT-3 model as it was the biggest available language model at the time of this project. It is a transformer model made for text completion. It works by giving the model a text prompt, which it will then complete by predicting the next words. For example, one could ask GPT-3 to create a list of 3 questions for my interview with a science fiction author. And GPT-3 would generate a list of sensible questions like, what inspired you to write science fiction? Or what themes or topics do you explore in your stories? But we can also use GPT-3 to answer questions like asking who was the president of the United States in 1955. And GPT-3 will complete the text with the answer, President Eisenhower was in office during 1955. Notice that there's a question-answer example to prime the model on the task. Based on this model, we asked now whether we can use GPT-3 to generate semantic features, and if yes, how similar or different the semantic knowledge of GPT-3 is compared to humans, and whether they have human-like quality. So how does it look like to ask GPT-3 for semantic features? For this, I prepared a short demonstration from GPT Playground. Here, I first asked GPT-3 what are the properties of a cannon. And the first generated answer is, some of the properties of a cannon include that it is a large weapon that fires a heavy projectile. It has a long barrel and it is mounted on a carriage. This answer is quite good already and makes sense also with respect to the prompt, but it is not structured enough so that we can create a feature norm out of it. Therefore, we give GPT-3 the true answer as a hint on what we expect as the output. The example from McRae then contains features like it is large or it is a weapon. Or it is made of iron or it is powerful. On the next try, GPT-3 still does not generate the expected output, but after the third example, it works. This so-called few-should learning enables us now to prime GPT-3 to generate structured semantic features. And after the priming, we can generate features for arbitrary concepts. For example, by asking what are the properties of an abacus. And GPT-3 will now say it is used for counting, it is a mathematical tool, and so on. To create a new feature norm, we chose the Things database of 1,854 real-world object concepts, covering a broad range of living and non-living concrete objects. The database is complemented by similarity ratings for all concept pairs, which we later use for external validation. We repeated the feature generation process 30 times to reduce the bias coming from the priming examples and to mirror experiments with multiple human participants. Each repetition used 3 different priming examples from the McRae feature norm. As the generated answers are text, we had to process it to extract and norm the features. We applied several splitting and extraction rules that transform, for example, the answer, it has fur, it is a mammal and it barks, to the features, has fur, is a mammal and barks. We further normed the features to be as concise as possible. For example, a feature like it is a small animal gets transformed to is small and is an animal. The processed feature norm still consisted of rare features that we filtered out, similar to the approach by the McRae feature norm. We removed features that occurred in less than 4 repetitions. Using this approach, we decrease the sparseness in our feature norm, but keep unique features within concepts. In the end, the produced semantic feature norm consisted of over 120,000 features in total. So does GPT-3 generate features similar to humans? Here you can see 5 most frequent features for dog and scarf generated by GPT-3. And on the left side, you can see human-created features. We can see that both GPT-3 and humans use similar features. For example, has a tail for dog or is long for a scarf. Next, we asked whether the GPT-3 generated features follow a similar distribution to human-created features. For this, we manually labeled a subset of features into the categories encyclopedic, taxonomic, conceptual, visual, perceptual, and functional. And here in the plots, we can already see the relative number of features per label for the McRae, CSLB, and GPT-3 feature norms. We can further see little differences between the human-created norms, but also a strong similarity between the McRae and the GPT-3 norm. Most features in both norms are encyclopedic or conceptual. This is kind of expected as we use the McRae features for the priming of the model. In the next slides, I will use the term similarity. So let me quickly introduce how similarity is defined here. First, we use the count frequency of features per concept as a concept representation. For example, we can define the concept dog with the counts of the features is a mammal and has fur. Then we can use cosine similarity as the similarity metric. This would lead, for example, to 0 for dissimilarity between dog and scarf. Based on this similarity, we asked how similar the superordinate category structure is between GPT-3 and humans. For this, we use the categories land animals, clothing, birds, vehicles, fruits, and musical instruments. Here in the similarity matrix, we can see the similarity from 0 to 1 for all concept pairs within and between categories. And we can see a clear structure with high similarities within categories and low similarities between categories. Also, it is similar to the structure we can find in the CSLB feature norm, with small differences, for example, in clothing or between vehicles and music instruments. Next, we looked at all concepts belonging to the categories and quantified the category structure. For this, we calculated the similarity between all pairs within a category and subtracted the mean similarity of all pairs between categories. We can see the results for the McRae norm in green, for CSLB in blue, and GPT-3 in red. The mean similarity of GPT-3 generated features is similar or even higher for the categories land animals, birds, vehicles, and fruits, and lower for clothing and music instruments. We further looked at the overlap of concepts in all three feature norms and looked at the representational similarity. For this, we calculated the similarity between all pairs of 300 concepts and calculated the Pearson correlation. As you can see, the correlation is quite high between the McRae and CSLB norm, but also between the McRae and GPT-3 norm, as well as between the CSLB and GPT-3 norm. Next, we ask how well external human similarity and relatedness ratings are represented in the feature norms. For this, we use the similarity ratings from Similex 909 and Things, and the relatedness ratings from MEN. In the table, we can see the Pearson correlation for concept pair similarities. The CSLB feature norm has the highest correlation with the Similex 909 and Things similarity ratings, whereas the GPT-3 norm has the highest correlation with the MEN ratings. But overall, the performance is quite similar across all norms, indicating a similar quality of features. Yet we can see higher correlations compared with the McRae norm that was used for priming. To explore whether the similarity is based on similar information, we performed a variance partitioning analysis. On the left side, we can see the variance partitioning between CSLB and GPT-3. The shared explained variance is quite high, and the unique explained variances are relatively small. On the right side, we can see the variance partitioning between McRae and GPT-3 with similar results. Overall, there's a strong overlap in explained variance between GPT and human-generated norms, supporting the idea that they are using a similar information for similarity prediction. In summary, the results show that humans and GPT-3 rely on similar conceptual knowledge for producing concept features, and that we can use GPT-3 to automatically generate features for arbitrary concepts. This approach might also be useful for other behavioral tasks too, not only semantic feature collection. We further provide a semantic feature norm for 1,854 object concepts generated with GPT-3, which may help improve our understanding of object knowledge and object representations. Future work could further investigate the effect of the datasets used for priming, as we saw that it might bias the results. One could try to use other norms or to try to force GPT-3 to generate only features of a specific type, for example, visual features. One could also look at more abstract concepts and what features GPT-3 would generate. For example, we already tried to generate features for concepts like democracy and intelligence with interesting results. For example, democracy is described by is fair and is a form of government. And with this outlook, I want to thank you for your attention. If you're interested in the code and the feature norm, you can find them both online by following the QR codes.